Hello everyone, this is Dr. Lennon, and we are going to go over the test review today. So let's start with this first problem. We're just finding the equation of a line that passes through 2 points. So we just go ahead and first find the slope. So we do that using y2 minus y1 divided by x2 minus x1. So I have 5 minus 4 in the numerator, and then 8 minus 3 in the denominator, and I get a slope of 1/5. So then my line has to look like y equals 1/5 x plus b, which is the y-intercept. So plug in either of those pairs of points to figure out what b is. So I'm just going to plug in 3 and 4. So 4 replaces y and 3 replaces x. So we get 4 equals 3/5 plus b. And we want to subtract 3/5. So we end up with 17 over 5 is the value of b. So our line has equation y equals 1/5 x plus 17 over 5. And that's it for that one. Again, this is just pre-calculus review, but it does come up quite a bit because essentially the derivative is based on the average rate of change, which is kind of a generalization of slope. Anyway, let's go ahead and move on to the next one. Okay, for number 2, we have 2 factoring problems. So to solve the first one, we can just use it's really quick because that's all we have to do is identify 2 numbers that multiply to the constant term -15 and add up to the middle coefficient of 2. So x plus 5 and x minus 3 do the trick. And then we just set each linear factor equal to 0 and solve by the zero product property. So we have our 2 answers, x equals -5 or x equals 3. So that's it. Part B is a little longer because the coefficient of x squared is not 1. So if we look at part B, we have 5x squared plus 13x plus 6 equals 0. So what we have to do is we have to start by taking 5 and 6 and multiplying them together. So we get 30, and what we want is ideally 2 numbers that multiply to 30 and add to the 13. So 10 and 3 will do the job there. And then we split the middle term. Essentially 10x plus 3x is the same thing as 13x. That's what we're using those for. So we can rewrite the polynomial is 5x squared plus 10x plus 3x plus 6 equals 0. And then we can factor by grouping. So we look at the first pair of terms, 5x squared plus 10x, and we can take out the greatest common factor of 5x, and we get x plus 2. And then from the second pair of terms, 3x plus 6, we can also take out a 3 and be left with x plus 2. So this gives us our factorization, 5x plus 3 times x plus 2. So then we set each one of those linear factors equal to 0 by the zero product property and solve. So 5x plus 3 equals 0, or x plus 2 equals 0. So we get our 2 answers here, x equals -3/5, or x equals -2. So those are the 2 answers there from factoring. So the first one, again, you can use the shortcut method with because the coefficient of x squared is 1. The second one, we have to use the factoring by grouping method. So let's move on to number 3. Okay, for number 3, we want to find an exponential function through 2 points. So we're just going to use the standard form here. So an exponential function in standard form just looks like y equals a times b raised to the t power. And we want to plug in both points. Well, actually, in this case, it's even simpler than that because we know 0, 7 is the y-intercept. So that means that's the value of a. So y has to be equal to 7 times b to the t because 0, 7 is the y-intercept and a is always the y-intercept. So now that's all we have to do is plug in our other point into this function. So replace y with this 9.2575, and t will become 2. So we get 7 times b squared, and then we can just solve for b. So divide both sides by 7, and then take the square root. So if you plug that into your calculator, we get 1.3225 equals b squared. So take the square root of that. Again, b has to be positive, so we don't have to worry about any negative values there. So we get b is equal to 1.15. So our exponential function is y equals 7 times 1.15 to the t power. And that's the exponential function. So similar to linear functions in that there are two parameters we have to solve for, so we have to use both points, plug them both in. Okay, let's move on to number 4. So for number 4, we're just trying to write as a single logarithm here. So essentially we're going to be looking at two of the properties. So the properties we have, well actually there's 3 of them if you want to specify all 3, but we had, if you have the natural log of say m plus the natural log of n, this is the natural log of m times n. If you subtract them, that changes to division. Natural log of m minus the natural log of n is the natural log of m over n. And the third one with powers, if you have the natural log of, say, m to some power p, you can take that power and bring it in front, p times the natural log of m. Now, for this one, we're not, we're going to be using them kind of, we're starting with property 3. We can't combine the logarithms until there's nothing in front of them. So that's the first thing, that 5 natural log x plus minus 3 natural log w plus the natural log of y. We want to start by making 5 the exponent in the first one and 3 the exponent in the second. And then what we can do is we can actually put them together via the addition and subtraction. So this will end up being the natural log of x to the 5th times y over w to the 3rd power, utilizing properties 1 and 2. And that's it. That's what you had to do to write it as a single logarithm. So let's move on to number 5. Okay, so for number 5, we have 5 raised to the 2x plus 1 equals e raised to the 7x. So we want to solve for x. So the first thing we need to do is take a log of both sides. So let's take natural log because it'll cancel on the right hand side with the exponentiating by base e. So on the right hand side we'll just be left with 7x, and on the left hand side we can bring down the 2x plus 1 in front, and we'll just have the natural log of 5. Now usually I would just keep natural log of 5 and wait until the end to round, but I found that a lot of students prefer just working with decimals. They're less error prone. So I will go ahead and just put natural log of 5 in my calculator and round that to say 1.61. And then this just becomes a linear equation with regular numbers. So the natural log of 1 has value 1.61. And we can go ahead and multiply through. So just distribute the 1.61, and we get 3.22x plus 1.61. And that equals 7x. So then just subtract 3.22x on both sides. So we get 1.61 equals 3.78. Then we just go ahead and divide by that 3.78, and we get our final answer. So x is about, again, we did round, so keep that in mind. About 0.43. But basically just taking the natural log and making use of its properties. And that's it for that one. Okay, for 6, we're trying to find the average rate of change of this population function that's modeling bacteria growth and thousands of bacteria, and time is in hours. So let's just remember the average rate of change formula is basically given by f of x2 minus f of x1 divided by x2 minus x1. So first thing we need to do is find both of the y values, so p of 3.5 and also p of 2.5. So we're plugging them into the exponential function that's given there. 5.4 times e to the 0.4 times 3.5. So we want to find this value. And same for 2.5. So let's go ahead and do that. So we get about 21.90 and 14.68. And then what we want to do is we want to just find the average rate of change using those numbers. So it's essentially just the slope formula. So we get 21.90 minus 14.68. And we're actually dividing by an interval of length 1, so we're not going to really have to do any real division. So that comes out to 7.22. So then we want to be sure to interpret those results, so let's go ahead and do that down below. Okay, so basically during the interval from t equals 2.5 to t equals 3.5, the bacteria colony increased on average by 7.22 thousand per hour. Remember, the average rate of change, just like a slope, is always interpreted as a rate, so it's the rate of the output per rate of the, it's the units of the output per units of the input, and that's what gives you the rate. All right, so let's go ahead and move on to number 7. Okay, so for number 7, we're just evaluating some limits based on the graph here, and remember, the limits are essentially where the graph is approaching, not where the actual value is. So the first one is saying, so again, just recall if you have the limit, let's say the limit, well, let me just write it as, so you have one-sided limits, so we probably didn't talk about those too much, but let me just explain now. So if you have the limit as x, if you have this notation of the limit as x goes to a from the right, you're only tracing the graph on its path from the right to the left. So you're not looking left of the value you're concerned with at all. And if it's written like this with a superscripted minus sign, this means from the left. So you're tracing the path from the left to right side. So this graph here, if we're approaching the x value 0, we're following the line from the left-hand side till we reach that open dot with a y value of 2. So that's the value for a. The limit actually is just equal to 2. Oh no, sorry, I did from the left. From the right, it's actually the same. Sorry, I don't know why I was going left or right. From right to left, you trace the path, and you are still just right there at 2. Actually, since the limit from the right and the left is exactly the same, the two-sided limit will exist there. For b, we're looking at the limit as we go to 1. So the x value 1, we're tracing the graph from left to right, and we're following the graph till we get down to the lowest open dot there, and that's going to be -1. Similarly, if you would look at the path on the other side from right to left, the right-sided limit as x approaches 1 of f of x would actually be 0 here. So, and if you look at, for c, f of 1, so neither the right nor the left limit is actually the function value, because the function value is where the graph appears. If it's a continuous function, those things coincide, but it's not. We have a removable discontinuity here. So the closed dot on that vertical line x equals 1 is going to be the y value, so that's what we evaluate f of 1 as, and that is actually the value 2. And for part D, looking for the limit of f of x going to 1, from the left we said it was -1, from the right we said it was 0. Since the two-sided limits, or since the one-sided limits do not agree, no two-sided limit exists. So for part D, the answer is actually does not exist, which we often just abbreviate with capital D and E. So the two-sided limit as x approaches 1 does not exist on this graph. All right, so let's move on to 8. So for 8, we want to compute this using the definition of the derivative, so that's the limit definition. So f prime of x here, remember it's going to be the limit as h approaches 0 of f of x plus h minus f of x divided by h. So we're replacing each occurrence of x. There's only one in the formula with x plus h in parentheses. And our goal is to cancel that h in the denominator. So we have 3 times x plus h quantity squared minus 1, and then we need to subtract the formula of f of x, which is just 3x squared minus 1, with everybody being divided by h. Okay, so we want to expand now, and hopefully some terms will cancel in the numerator. So we get 3. Remember to FOIL out x plus h to get x squared plus 2xh plus h squared minus 1, and then distribute the negative, so minus 3x squared plus 1. So immediately the minus 1 and the plus 1 cancel. So let's see what terms are left. We have the limit as h approaches 0. So we have 3x squared plus 6xh plus 3h squared minus 3x squared. And now the 3x squared terms cancel. So we'll have the limit as h approaches 0 of 6xh plus 3h squared over h. And h can be factored out on top. So we have h times 6x plus 3h. I know you can take out a 3 as well, but we just want to cancel the h. That's why I'm only taking out that. And then we plug in 0 for the remaining h, and we're left with just the answer, which is 6x. But when using the definition, it's important to write down the limit and show all that work. Okay, so let's move on to the last two, which are just doing derivatives but using the shortcuts. Okay, so for number 9, we have this function f of x equals 8x cubed minus 5x plus e squared. So the thing about e squared is it's just a number, so we want to remember some of our derivative rules. The main one is if you have x to the n and you take its derivative, you get n times x to the n minus 1. And then also if you would have, say, a constant times x, the derivative of that is just a constant. And if you have a derivative of a constant by itself not being multiplied with any function of x, that has derivative 0. So you can go back to the derivatives video to review that if you want, but those are the 3 rules that I'm using here. So when finding the derivative f prime of x, that first one, the derivative of x cubed, we apply the first rule, and that's going to be 3x squared. So we basically get 8 times 3x squared. Minus 5x would be rule number 2, so we just get the minus 5. And e squared actually has derivative 0, right? E squared is just a number. You could type it into your calculator. Cleaning that up a little bit, we would actually write it as 24x squared minus 5, and that would be your answer on this one. Number 9 is very similar, but we just have to do a little algebraic kind of pre-processing. Okay, so for 10, g of x, if we write it out using the usual fraction notation, it looks like 7x squared minus 3 over x. So what we have to do here is we just want to separate it and rewrite it using exponent notation. So this can be rewritten as 7x squared over x minus 3 over x. So the 7x squared over x simplifies to 7x, and then the 3 over x can be rewritten as 3x to the minus 1. And then we're just going to use the rules from above to find the derivative there. So the derivative of 7x is just 7, and then for the other one we want to bring down the negative 1, and then multiply by, and then subtract 1 from the exponent. So negative 1 minus 1 is negative 2. So the derivative just simplifies to 7 plus 3x to the minus 2, or if you prefer, you can write that as 7 plus 3 over x squared. So that is it for number 10. So that's the test review. Again, a lot of pre-algebra concepts on this one, and then we finish with just taking some derivatives. Please let me know if you have any questions. Otherwise, this is Dr. Lennon signing off.